What we want to talk about now is known as Gibbs free energy. It's named for Josiah Willard Gibbs. Let's review the second law. The second law of thermodynamics says that for any process that is spontaneous, that the increase in the entropy of the universe must take place. That is an absolute necessity for a process or a reaction to be spontaneous. But we know that there are some spontaneous processes that result in a system with lower entropy, and we've explored that. So when a liquid freezes, it becomes more ordered. Its system has a lower entropy because it's more ordered. It has to give up heat in order to become more ordered. And that heat radiates out from the system into the surroundings, and it increases the entropy of the surroundings. So the second law of thermodynamics simply says that the total entropy, which is the entropy of the universe, is the sum of the entropy of the surroundings plus the entropy of the system that we're specifically studying. So we study the system, but it either increases or decreases the entropy of the surroundings, and the total entropy of the universe is the combination of both the system entropy change and the surroundings entropy change. The change in entropy of the system is easy to calculate. You've actually done it already. If a reaction is exothermic, that means it's given off heat to the surroundings. If the surroundings have acquired heat from the system, then that increases the change in entropy of the surroundings. You have a positive change in entropy for the surroundings. So we can express that as delta S for the surroundings is equal to minus Q for the system divided by the absolute temperature. And if we're doing all of this under conditions of constant pressure, then the delta S for the surroundings is equal to the negative delta H for the system divided by the temperature. And what we're going to do is we're going to substitute this term for the delta S of the surroundings just to get everything in terms of the system. The delta S total, the delta S for the universe, is equal to delta S for the surroundings plus the delta S for the system. We make the substitution and we get delta S for the surroundings is equal to minus delta H for the system divided by the absolute temperature. Thus, we get delta S for the universe is now equal, after the substitution, to the minus delta H for the system divided by the absolute temperature plus the delta S for the system, the change in entropy for the system. For no apparent reason, let's multiply both sides by minus T. And when we do so, we get minus T, delta S for the universe is equal to delta H for the system minus T delta S for the system, which leads us to minus T delta S is defined as the Gibbs free energy, G. So here we are with the Gibbs free energy. So here's what I want you to remember. Minus T delta S in this equation is equal to the change in Gibbs free energy. What does that mean? Well, if the delta S for the universe, and that's what this delta S is, but it's being multiplied by minus T in the equation I'm about to present to you. So if delta S is positive, multiplying it by minus T will make it negative, and you'll have a negative delta G. And that leads us to this. For a process at constant temperature and pressure, the delta G for the system is equal to the delta H for the system minus T delta S for the system. What we've accomplished here is we've turned everything in terms of the system now. So when we're studying a particular system and we want to know whether that system is going to have a spontaneous process or not, all we have to do is look at the delta G, which is equal to the delta H for the system minus T times the delta S, the change in entropy for the system. Memorize this equation. You will need this equation. Everything is defined in terms of the system. It's easy to calculate. So if delta G is less than 0, that is, it's negative, the process is spontaneous in the forward direction because the delta S of the universe is positive. You've increased the entropy of the universe, which is absolutely necessary for a process to be spontaneous. If delta G is positive, a process is non-spontaneous in the forward direction because delta S for the universe in the forward direction is less than 0, and no spontaneous process can occur where the delta S of the universe is a negative value. What this does mean, if delta S for the universe in the forward direction is positive, that means delta S for the universe is negative in the reverse direction. And if delta S for the universe is negative in the forward direction, it means that delta S for the universe is positive in the reverse direction. Finally, we come to this. If delta G equals 0, the process is at equilibrium. It's at that place where the reaction is neither spontaneous in the forward direction or spontaneous in the reverse direction. Equilibrium. Delta G equals 0 at equilibrium. All right, here we go. So temperature and spontaneity. You may have already guessed, spontaneity is temperature dependent. After all, temperature is a term in the Gibbs free energy equation. And if temperature is a term in the Gibbs free energy equation, you know that temperature matters in the matter of spontaneity of a given process. So consider the signs of delta H and delta S would always seem to be in some sort of conflict determining whether a reaction is spontaneous or not. Now let's take a look at the relationship between temperature and spontaneity and ask ourselves, under what conditions is delta G negative? That is, under what condition is a reaction spontaneous? If we look at the equation, delta G is equal to delta H minus T delta S, what we immediately see is the delta H is at war in some instances with the delta S. Most spontaneous processes are exothermic, which would make delta H a negative value. Most processes that are spontaneous would increase the entropy of the system, which would make delta S a positive value. So in this instance, if I have a negative or exothermic delta H and a positive change in entropy, increasing the disorder of the system, I have a negative value minus a positive value. And a negative value minus a positive value will always result in a negative value. And if I have a negative value, if my value winds up being negative for delta G, then my reaction is spontaneous regardless of what the temperature is. It doesn't matter what the temperature is. My reaction will be spontaneous at all temperatures if delta H is negative and delta S is positive. That is, they are opposite in the correct direction. On the other hand, if they are opposite in the incorrect direction where I have a positive delta H, that means my process is endothermic and my delta S is negative, meaning my system becomes more ordered. Now I have an endothermic process which is causing the system to become more ordered. That reaction will never happen. It will be non-spontaneous regardless of what the temperature is. Completely non-spontaneous no matter what the temperature. Now we get to the difficult part. We don't know whether this reaction will be spontaneous because we have the same sign for both delta H and delta S. Delta H favors spontaneity if it's a negative value. Delta S does not favor spontaneity if it's a negative value. Mathematically, we have a negative minus a negative, which is a positive. So what we want to do is we want to minimize this negative, this unfavorable negative value for delta S by minimizing the temperature, by having the temperature be as low as it possibly can, relatively speaking. So if the temperature is low enough, the negative delta S will be overpowered by the exothermic change in enthalpy. So the reaction will be spontaneous at low temperatures if we have a negative delta H and a negative delta S. And finally, we get to the final combination where we have a positive or endothermic delta H and a positive or increase in entropy delta S. We have a positive minus a positive. Well, a positive minus a positive will only result in a negative value for the delta G if the temperature is very high. We need to magnify that positive delta S by having a really high temperature so that when we subtract the positive delta S from the positive delta H, the positive delta S value is a larger value. So that reaction will only produce a negative delta G and a spontaneous process at very high temperatures. What we want to do now is determine the precise temperature at which a reaction will actually become spontaneous. And what I want to draw your attention to is a diagram that I use quite often, and it's an energy diagram, and this time with respect to the Gibbs energy of this particular reaction. We have reactants over here on the left indicating that if the reaction is moving in this direction, it's moving forward. We have products over here on the right indicating that if the reaction is moving in the reverse direction, it's moving from products to reactant. In the middle, at the minimum amount of energy, we have delta G. And delta G at the minimum amount of energy, which is delta G equals 0, is at equilibrium. That's where the forward reaction is, the rate of the forward reaction is equal to the rate of the reverse reaction, and the reaction is non-spontaneous in either direction. Now we know from previous examples that if delta G is less than 0, it's a negative value, that the reaction is going to be spontaneous in the forward direction. If delta G is greater than 0, it's a positive value. That means the reaction is non-spontaneous forward, but it is spontaneous in the reverse direction. And all reactions, whether spontaneous forward or spontaneous reverse, head toward equilibrium where delta G is equal to 0. And this is the temperature. The temperature based on delta G equals delta H minus T delta S. This is the temperature at which a reaction can become spontaneous. If we use our delta G equation, delta G equals delta H minus T delta S, and we understand that the reaction will become spontaneous at equilibrium, that's the beginnings of spontaneity for a reaction, we can solve for temperature. And if we solve this equation for temperature, we get T, the temperature at which the reaction becomes spontaneous, is equal to the delta H divided by the delta S, the change in enthalpy divided by the change in entropy. Keep in mind that delta H is usually in kilojoules and delta S is usually in joules per Kelvin. So change one of them, either change to kilojoules or change to joules, but both of these terms need to be in the same units before you do your calculation if you're going to get an actual or an accurate temperature at which the reaction becomes spontaneous. Let's review. Remember from Chemistry 1 that the delta H under standard conditions can be calculated based on the sum of the delta H of formation of products minus the sum of the delta H of formation of reactants. Delta H of formation is the standard enthalpy of formation of chemical species from their elements in their standard states. Standard molar entropy is the standard entropy of the species. Recall that the standard molar entropy is not equal to zero for pure elements in their standard states. All standard molar entropies are positive values. The process for calculating delta G, similar to the calculation for the process of calculating delta H under standard conditions and delta S under standard conditions, you can simply use the tables for the delta G of formation under standard conditions. That's the standard Gibbs energy of formation of a chemical species from its elements in their standard states. Again, just like delta H, elements in their standard states will have a delta G of formation that is equal to zero. So O2, Cl2, F2, iron, aluminum in their standard states does have, or they do have, delta G of formation that's equal to zero. Values of delta G of formation under standard conditions can be found just like standard molar entropy and the delta H of formation. So now let's use the tabulated values for the delta H of formation from the tables and the delta G of formation from the tables to determine the standard entropy change for the following reaction in joules per Kelvin. So first of all, let's remind ourselves that we have delta G is equal to delta H minus T delta S, an equation you need to know. And we're doing all of this under standard conditions, which is why I put the little zeros up there. They mean standard conditions. Let's go ahead and solve this problem for the delta S of formation. The first thing I want to do is add T delta S to both sides. So we'll have T delta S plus the delta G is equal to delta H. And then I'm going to go ahead and I'm going to subtract delta G from both sides. And what that gives me is T delta S is equal to delta H minus delta G. And then finally, we're going to go ahead and divide both sides by the temperature, T. And what we wind up with is delta S is equal to delta H minus delta G divided by the absolute temperature. So all I need to do is use the tables to determine the delta H for the reaction under standard conditions, the delta G under standard conditions, and I know that the reaction is being done at 298 kelvins. All right, so here we go. So using the tabulated data above, the delta H for the reaction under standard conditions will equal the sum of the products minus the sum of the reactants. And for my reaction, I have the reactants, carbon dioxide, and carbon dioxide, the delta H of carbon dioxide, and there's only one of them, is minus 393.5, plus, and I have two liquid water, so that'll be 2 times a minus 286. Close that off. There are my products minus my reactants, and my only reactant that I have to worry about is the methane, and that's a minus 75. Just for consistency, since I have 2 oxygens, I'll remind myself that oxygen has a delta H of formation that's equal to 0. And when I come out with the delta H, I come out with a minus 890.5 kilojoules. That's 890.5. So all that's left is go ahead and calculate the delta G under standard conditions, which will be minus 394 plus 2 times minus 237, and that minus a minus 54 plus, again, 2 times 0, the delta G of formation of oxygen. And when I do that, I get a minus 814 kilojoule. Finally, I'm going to go ahead and I'm going to retrieve this equation right here and simply plug these two values and the temperature in. And when I do that, I get a delta S that's equal to my delta H, which is minus 890.5 kilojoules minus a minus 814 kilojoules divided by my temperature of 298 Kelvin. And when I get that result, I get 0.257 kilojoules per Kelvin. Since we normally report delta S in joules per Kelvin, I'll convert that to joules per Kelvin, which will be 257 joules per Kelvin, and that is my solution.